I'm Mark Hempsell, and I must say that I'm very flattered to be invited to give a second contribution to this BIS-Italia series of evening technical talks. Last October, I published a paper in the Society's Journal on the Scorpion, which is a concept design for a multi-purpose spacecraft capable of operations from low Earth orbit out to as far as Mars and Venus. Since then, there have been articles in both Spaceflight and Room magazines and a BIS webcast video talk. The publicity around these has generated a few queries and comments. Now, some of these are just questions about features of the design, but some are questions and comments that relate to its role as a component of the space infrastructure. Well, this is hardly surprising, as the Scorpion project was intended to demonstrate the scope of the space infrastructure that our current technology could create and then explore its potential. And of course, in doing this, it inevitably raises interesting points about the space infrastructure generally, and I'd like to address three of these issues this evening. But let us start by making it clear what the space infrastructure is. Now, as an Englishman, it pains me to admit that the word infrastructure is of French origin, although its root is Latin, and it means the underlying physical and organisational structures and facilities that are needed for the operation of an enterprise. So in the context of space, it means all those things that enable space activity to take place. And clearly the key and most important is to have a launch system. Otherwise, you cannot reach space at all. And so without one of these, there cannot be any space flight. Now, if you have a launch system, then you have to have a place to operate it from. So you must have a launch site. And of course, you will also need a place to build and test both the launch system and the payload. And once the payload is in space, then it needs to be tracked and controlled, and there must be a means to communicate with it from the ground. So the basic infrastructure shown here is needed for any space activity. Every spacecraft and satellite, from the simplest CubeSat to the Apollo moon landings and Hubble Space Telescopes and interplanetary probes, all have these infrastructure elements supporting them. And if you want some degree of control and autonomy in your space ambitions, then you need a degree of political control over all these elements, an obvious truth that escaped the British government for half a century. Okay, that outlines the must-have elements to support space activity, and it dates back to Sputnik 1. But consideration of these as being within a concept of an integrated space infrastructure did not come about until that infrastructure extended into space. This expansion into orbit is a process that started in the 1970s with the establishing of the first space stations. These provided basic support platforms that could enable a wide range of activity, which was not really practical by any other means. But it was actually in the 1980s, when the Space Shuttle system was coming into operation and the tracking and data relay satellites were launched, that the term space infrastructure starts to appear in the literature. Mostly in the context of the Space Shuttle and how it was going to interact with the space station that was then in the early stages of its development. And so what constitutes the space infrastructure today has a significant in-orbit component. Some of this is very well established, such as tracking and data relay, and of course space stations, which are now decades old, are widely used. In-orbit servicing has a more patchy history, with human servicing from the shuttle now no longer a possibility. But new geostationary satellite servicing systems are starting to become a reality with the attachment of Northrop Grumman's mission extension vehicle to Intelsat 901 this April. The orbital transfer stage is the least evolved of the in-orbit infrastructure services, and indeed it could be argued that it has not yet been properly realised. Stages, like the Russian Fregat, have a lot of features of such a system, but they still operate as sophisticated upper stages to launch systems rather than a separate system based in orbit and then used as needed. An orbit transfer stage is a space-based reusable system used to transfer payloads from low Earth orbit to higher Earth orbit and interplanetary orbits. Now that's my definition for this talk, and it is normally, but not always, what people mean when using the term. The theory is that you gain from various efficiencies that are fundamentally due to the separation of reaching orbit and moving from one orbit to another into two separate functions, with specialised vehicles which can be better optimised for their different roles. These efficiencies include only the transfer stage's propellant needs to be launched for each mission, not the whole stage. So the whole mass that needs to be launched for each mission is reduced by around 10%. The launch system can be smaller as the payload and the propellant can be launched separately, and by smaller I mean maybe half the size. The engine thrust can be lower than 1 Earth gravity, which saves engine mass and saves structural loading and hence structure mass. High exhaust engine options become viable, like the nuclear engine we're about to see, or electric propulsion. And further, there is no need to design for aerodynamic flight, so the structure can be lighter and more efficient. Of course, there's a big downside to an orbital transfer system, and that is that they require an orbiting spaceport in low Earth orbit from which to operate. And this means they only make sense when the traffic volume is large, which is one of the reasons that we haven't seen them yet, at least in the form that I'm outlining here. So what is the Scorpion's infrastructure role? Well, fundamentally, it is an orbiting transfer vehicle, but it's a bit more complex than that when you look at the detail. I think the good comparison here is the Space Shuttle. That was also primarily a transport system, but it had the means to undertake servicing in orbit, and it had what was effectively a small space station in the crew cabin. And the Scorpion is the same. And here we have an extra bonus. Having the habitation facilities and the servicing kit like manipulators integrated into the Scorpion means that unlike a pure orbital transfer stage, it does not need to be based at an orbiting spaceport. Just before going on to look at the detailed issues, I think I should highlight the importance of this sort of development of the space infrastructure. Judging from the reactions to the papers and the videos, many people find the Scorpion an inspirational concept, and I freely admit that creating a system with spectacular features was part of my intent, so I'm glad the wow factor is working as I hoped. So we're into what is often characterised as Buck Rogers, which has been used as a derogatory term for space science fiction and spaceflight that feels like science fiction since the 1950s. In 1979, Tom Wolfe published the novel The Right Stuff, which contained the memorable line, "No Bucks, no Buck Rogers," which so aptly sums up the NASA relationship with the US government in the Apollo era that I'd always assumed that it was of the period, and I only discovered while preparing for this talk that it was in fact invented by Tom Wolfe a decade later. Since then, the NASA government relation has not altered that much, and so this is still a widely quoted phrase, and it sums up an attitude that sexy elements of spaceflight like launchers and space station and crewed space vehicles have no intrinsic economic merit and are funded, mostly from the public purse, for their prestige, inspirational and even entertainment value. To illustrate this, I was in discussion in the 1980s with a quite eminent British space engineer about the UK getting involved in the space station programme, which was being characterised with that new term space infrastructure. His response was, "We should stay out of all that infrastructure stuff, it's all just prestige." I pointed out that space launch systems were part of the space infrastructure, and he started a response along the lines that they couldn't be infrastructure because they have a use, before pausing and realising that probably I was right. Well, at least he understood the need for a launch system. To give another example from around the same time, a civil servant in the British National Space Centre was presented with a rather elegant and impressive piece of British student rocketry. Well, he agreed that it was impressive, but then to dismiss it he said, "But I don't see the application." The perception that launchers, space stations and all the other Buck Rogers stuff are undertaken for soft objectives like prestige, inspiration, general technology advance and other rather vague and ill-defined reasons is still widely believed, particularly within governments, and this has led to some pretty silly space policies, not just in Britain, but across the world. Now for me, space infrastructure has always been the really interesting part of the space activity. Okay, partly because it is the Buck Rogers bit, but mostly because it is at the core of space activity, being the primary driver of its costs and its capabilities. And those are what I'm interested in improving. Because if we do not improve them substantially from this current limited form, we're never going to get to advanced the applications such as power satellites, space tourism, space resource utilization, space manufacturing, and so on. So let me make an argument. Because the space infrastructure is by definition the fundamental basis of space activity, and given the very high economic value of space, I think it would be far more accurate to say no Buck Rogers, no bucks. So I have no guilty feelings and make no apology about getting excited at sexy pieces of space infrastructure as long as they offer an improvement in the support service. The more right the infrastructure is, the more bucks can be made, and that is a consequence of the increasing contributions space can make to human life. So let me start the detailed look at the issues with the key elements in any space infrastructure, the launch system. There were several comments on the video querying why Skylon was the sole launch system used by the Scorpion study, both for assembly of the vehicle and for its operations. There was even some suggestion that not including SpaceX was, and I quote here, a little like sour grapes. Well, the first reason that neither SpaceX nor Blue Origin were considered is that when the Scorpion work was started 6 years ago, neither of their systems had even been made public, let alone having user manuals showing how to use them. Whereas with Skylon, I had a user's manual, and therefore I had all the details I needed to create the concept design. And I knew all the details were there because I wrote the Skylon user's manual and made sure they were there. But a second and more important reason was that the Scorpion is effectively an extension of the Skylon requirement validation studies that I had led at Reaction Engines. These studies were intended to make sure that we had included everything needed to ensure that Skylon could undertake any mission that could arise in the future. We did not want to be faced with an opportunity to return to the moon, or to go to Mars, or to start a major tourism industry, only to find we'd failed to incorporate the key features necessary for those roles. Now, these studies never really stretched Skylon, although they did result in some minor tweaking, like making the size of the side access doors compatible with a public access system. The Reaction Engine's work had gone much further than would normally be conducted in a requirements generation activity for a launch vehicle, but I was curious to see how much further I could push Skylon before its limitations started to show. So the Scorpion work was in part a personal exercise to satisfy this curiosity. And therefore a key reason for only using Skylon was because that was the only way to meet one of the study's objectives. But this use of Skylon raises interesting questions about the comparison of smaller, highly reusable single-stage systems that operate more like aircraft, which I'm going to call space planes whether they have wings or not, and the alternative of a large lift system which can get its cost advantage through scale effects. An assessment that is now helped by the fact that both SpaceX and Blue Origin are going down the heavy lift route with their BRF Starship and New Glenn. So we have systems which are at a similar development level to Skylon to compare with. And whereas any large launch system with many tens of tons payload can be called a heavy lift system, for this talk I'm going to consider a more specific approach where the inherent size cost advantages are supplemented by at least some reusability to further reduce costs. Partly because both SpaceX and Blue Origin are doing this, so that is a fair comparison point, but also because the costs of a heavy lift system must be approaching the spaceplane costs, or the system will not be economic and there is no point in even considering it. Now, if you can only develop one system, then this should be the spaceplane, because the cost, reliability and availability requirements can only be met with a fully reusable single-stage to orbit vehicle. And at the moment, the best and indeed probably the only option is Skylon. And with the expectation that Skylon would be the only launch system in the infrastructure, that is the logic behind the payload sizing of around 15 tons to a 300-kilometre circular orbit. It was selected to ensure that it can capture the complete market for launches, in particularly the launching of large geostationary communication satellites. The alternative, that is developing only a heavy lift system, is more problematic, as it must incorporate all of the features that I've just outlined for the spaceplane, and this is far more difficult to do in a multi-stage system with complex recovery procedures. So given what the stated long-term objectives of both Elon Musk and Jeff Bezos are, I'm afraid in my judgment they have chosen the wrong path to realise them and are making things more difficult for themselves than they need be. However, as both enterprises are based in the United States, the advice they would have been getting would have been based on a background of 2 decades of failed spaceplane attempts, either using pure rockets or scramjet propulsion. With so many failed attempts, it's perhaps not surprising that they both decided to try a different approach. Maybe the real lesson here is pay attention to what the whole world has to offer rather than just what your own country can do. However, let's play a what if. What if you can afford to develop 2 launch systems at the same time? That is both a space plane and a heavy lift vehicle. Now, this is a very big what if, as you're taking the launch acquisition costs from the $10 to $15 billion region to around $30 billion. However, if done correctly, they can powerfully supplement each other. So let's look at this mixed launch infrastructure. The spaceplane no longer has to try to capture the whole market, as the top end will be covered by the heavy lift vehicle. So it can be made smaller. And this is a double win, as it reduces its acquisition costs, which are higher for a spaceplane, but also means that when operational it will fly more often, which again helps the economics. In this scenario, I would be looking at a spaceplane payload of something between 7 and 10 tons. In a mixed infrastructure, the role of the heavy lift vehicle is primarily to launch the in-orbit infrastructure elements like space stations and orbital transfer systems. The logic being that the infrastructure elements can be launched whole or in many fewer pieces, and this reduces the in-orbit assembly costs, which can be very significant. It means that the heavy lift launch system can have a higher per kilogram launch cost than the space plane, while the overall cost of the activity are indeed lower. Because it's not launching crew or very high value payloads, you would not put a James Webb telescope on it, for example, there is less of a drive for a complete range of abort options, and the occasional loss can be accepted. Now, can I be clear here? By higher specific cost and lower reliability, I do not mean it can be as bad as current launch systems. I mean it can be a little worse than its spaceplane companion. Finally, there is also no requirement on the heavy lift vehicle to return the payloads, which is a great simplification for the overall system. So, if the Scorpion was to be part of an infrastructure that had a heavy lift vehicle within it, of course that's the way you would launch it. Apart from reducing the assembly costs, this would have several beneficial impacts. The Serpent engine could be launched in one piece. the overall mass could be a little lower. There could be a significant speeding up of the final assembly time with a reduction in risk. It probably could be built without an in-orbit assembly facility. That would save 1.3 billion just there. And it would also open up several interesting alternative architectures. Now, there is a second potential role for the heavy lift launcher, and that is the delivery of propellant. We have been here before with NASA's post-Apollo program plans, which was to have been based on a dual launch infrastructure. It would use the Saturn V as the heavy lift system for the infrastructure elements and the space shuttle with a payload of around 7 tons delivering everything else. So in NASA's plans, it would have been the space shuttle that would have delivered propellant, a reflection that the Saturn V was not in any way reusable and therefore had a much higher per kilogram cost. And that makes the obvious point, that which of the two systems is best to launch the propellant depends on which can deliver it at the lowest cost. So the question of whether the heavy lift vehicle is used to deliver propellants depends on how close its per kilogram costs are to the space plane. Now, once again, other factors due to scale economies mean that the heavy lift system does not have to absolutely match the space plane, but it does have to get much closer in this case. Well, so far so obvious, but the complicating factor is that in a working infrastructure of the sort that's being envisaged by the Scorpion study, propellant completely dominates the launch inventory. A typical Scorpion mission would require 43 propellant flights out of a total of a little over 50 support flights for each mission. So around 80% of the Skylon support flights for the Scorpion are propellant delivery. And the story would be similar for any advanced infrastructure that extends out to the moon and beyond. When you consider the complete inventory that the launch vehicle is being asked to carry, more than half the mass required to be delivered to low Earth orbit will be propellant, pretty much regardless of the propulsion technology being used for orbital transfer. Now, this domination of propellant in the launch inventory means that it would have a dominating effect on the economics of whichever system is used. Now, I can't answer this decisively as there are too many unknowns, but it may be that which of the space plane and the heavy lift vehicle you use could simply be a matter of choice, because the propellant carrying role in and of itself is sufficient to create the economic viability of either system. And if this is the case, then I would argue for the heavy lift vehicle. It reduces the number of flights needed and its lower reliability is not an issue, as this is the lowest value cargo in the manifest. The Scorpion study was not really trying to find the optimum infrastructure solution. What it was trying to do is assess the potential of an infrastructure that our technology could realise. Now, there may be aspects of this that seem beyond our current instincts, even fantastical. For example, using 50 Skylon flights for each Scorpion mission may seem a lot. But if we have aircraft-like operations, then we have to think more in aircraft terms. Each year, except this year of course, the International Astronautical Congress draws around 6,000 people together, almost all of whom arrive using aircraft. If we assume that is 120 people per aircraft, typical of a Boeing 737 or an Airbus 320, that is 50 flights. And no one questions the viability of the Congress due to its demands on air traffic infrastructure for 50 flights. The Scorpion study confirms and extends the conclusions reached by the Skylon requirements validation studies about 5 years ago. That Skylon can operate as the sole means to reach orbit without constraining space activity. In the Scorpion study, I've explored scenarios of hundreds of millions of people living in O'Neill-like colonies in Earth orbit. And, for example, to provide a viable economic link between Earth and space for an in-space population of 500 million people would require around 6,000 Skylons, half cargo carriers and half passenger carriers. Now, this may sound a lot, but again, put it into aircraft terms. Both Boeing and Airbus have made around 10,000 737s and A320s each, so it's hardly a fantastical number. But to be clear, this conclusion that all you need is Skylon and Scorpion to completely open up space is not the same thing as saying that that's what the infrastructure should be. But it is an argument for improving the space infrastructure until it can provide what to all intents and purposes is a limitless capability. Then any new transportation systems, whether a launcher or an orbital transfer stage, can be judged economically as a means to do the same thing at lower cost, which has the effect of speeding up the growth of mankind into space. Which brings me to the second topic of this evening, the use of nuclear propulsion in space. It was the subject of a number of questions and comments and raises a wider question as to whether the use of nuclear power for propulsion in the space infrastructure is worth doing. The Scorpion depends upon a nuclear engine designed by Alan Bond, who also invented the Sabre engines for Skylon. It's called the Serpent, and it works by supplementing direct thermal heating with the hydrogen propellant with electrical arc heating. This produces an exhaust velocity in excess of 12.5 kilometers a second, considerably more than is possible with a conventional chemical engine or a simple nuclear engine like NASA's NERVA. It is the exceptional performance of the Serpent engines that enables the Scorpion to perform difficult missions like direct flight to the lunar surface and return. So the Serpent nuclear engine is the key technology for the Scorpion. Now, if it had been anything except nuclear, it would have been completely uncontroversial. But of course, it is nuclear, and as soon as you say the word nuclear, there is an emotional response related to its use on the Earth for terrestrial power and as weapons of mass destruction. I do not want to enter into the complex debate about the use of nuclear power on the Earth's surface, as I think it is irrelevant to discussion of the use of nuclear power in space. This is because the issues with the use in space are not the same, so it really is quite a different debate. The use that nuclear power is put to, the technology being employed, and the safety concerns are all unique to space. So let's start by having a quick look at those safety differences. I have seen an attitude that we should not be contaminating space as we have the Earth, as space is some sort of area of natural beauty that we could despoil. But space is not like a river valley or a great desert or a wide ocean. There is nothing there to despoil and contaminate except a lot of radiation. The point here is that space is already a high radiation environment, so nuclear systems are not really adding a new risk. Space is also very large, so isolating operations that are generating radiation is much easier. If we, for the sake of argument, want a separation distance of 5,000 kilometers, that's something like the radius of the Earth, then there are approaching 500,000 spaces in Earth orbit alone we could use. And most important is that there are no environmental factors that can transport the dangerous nuclear material and exacerbate any problems. The key issue with nuclear accidents on the Earth is radioactive material spreads into the biosphere quickly and over alarming distances. In space, there is no open biosphere and there are no transporting mechanisms. But there are also some downsides that make things more difficult. Firstly, there is no atmosphere attenuation, which at sea level provides more than a ton per square metre of blocking mass for each kilometre of separation, which can reduce the level of radiation an order of magnitude quicker than in space. Secondly, the radioactive material has to go on the launch system, raising the risk of contamination of the Earth's biosphere in the event of an accident. So we had better be using that ultra-reliable space plane. Although it should be remembered that the technology to ensure there is no radioactive leakage even in a launch accident has been well proven in the past with real events. Another technical issue is that on Earth we can solve shielding requirements by just pouring more concrete, but for space systems we cannot just throw mass at any shielding problems. So space is very different and should be treated as a separate issue. Now, there is one accepted application for nuclear power in space, which is the use of radioisotope thermal generators for missions that are so far from the Sun they cannot use it to generate electrical power or maintain a working temperature. An example of this, which has been widely used by NASA, is the General Purpose Heat Source, which has a little under 8 kilograms of plutonium-238, and that at the start of a mission can generate over 4 kilowatts of thermal power and 300 watts of electrical power. So assuming we continue to send spacecraft beyond Jupiter to the outer solar system, then the use of nuclear power at this level of complexity and scale will have to continue to be accepted. But I'm not going to be so silly as to say that since nuclear power is clearly okay for powering systems on deep space probes, that it is therefore surely okay for propulsion systems. The scale, the complexity of engines such as the Nerva engine shown here, or the Serpent engine, mean clearly we are dealing with a completely different set of concerns. Nuclear power has inherent dangers, as do all high-performance rocket systems because of the massive amounts of energy they generate. This is a subject we tend to forget, as with chemical engines, the energy comes from the propellants and we never have to directly address providing it. So who actually bothers to calculate how much power a large rocket engine is generating? Well, if you do bother, for a large launch system it is tens of gigawatts, well past the power of a large terrestrial power station and even exceeding the power requirements of a typical country. Let us look at this power issue in more detail. There are three technology candidates for propulsion on orbital transfer systems. Chemical, the technology most widely used at the moment, which can produce exhaust velocities from 3 kilometers a second for storable propellants like hydrazine and nitrogen tetroxide, up to 4.6 kilometers a second for a really good hydrogen-oxygen rocket. Then we have nuclear, the one I'm arguing for here, which can range from around 8 kilometers a second for a simple system like Nerva to 12.7 kilometers a second for the Serpent engine. And finally, electrical propulsion, another technology that is mature and now widely used and that can produce exhaust velocities that range from 20 to 50 kilometers a second. And as we all know, high exhaust velocity is good. It means we need less propellant to reach a given speed. But we also need thrust, and that complicates things. The power in rocket engines' exhausts is the result of just two things, the exhaust velocity and the thrust. If you set those two parameters, the power is determined and there's no way around it. So let's look at an example of a 200-ton thrust engine, the thrust of the Serpent that is used on the Scorpion. The chemical engines are under 5 gigawatts, but of course this doesn't concern us too much as this power comes free with the propellant. But as a matter of interest, rockets are very efficient systems, and over 90% of the available chemical energy ends up where we want it, propelling the spacecraft. The nuclear fission engines range from 8 to 12.7 gigawatts. These are also efficient engines because they directly use the heat produced by the reactor, but they are not as efficient as chemical rocket engines. For example, the reactor thermal power on the Serpent engine is 14.6 gigawatts, giving an efficiency of 87%. Finally, we have electric propulsion, where the spectacular exhaust velocity produces equally spectacular power requirements. And now the really bad news. The efficiency of these motors is around 60%, so the actual electrical power requirement will be more like 50 to 100 gigawatts. Further, electricity is notoriously inefficient to generate, So the energy consumption will have to be many hundreds of gigawatts, comparable to the power consumption of the United States. This is why electric propulsion operates at the sub-Newton level, because current satellites have available power levels that are in the kilowatt region. Now, for many applications, low thrust is quite usable, and indeed we now have operational all-electric satellites. So electric propulsion has a technology readiness level of 9. That is flight proven, as good as it can get. So why not use them on the Scorpion? To answer that, we have to look at the downside of using very low thrust propulsion. The first problem is that it can only be used to transfer from one orbit to another. To reach orbit in the first place, the engine thrust has to exceed the gravity force. Now, in the case of the Scorpion, it means using low thrust propulsion would mean it could not perform the lunar landing mission. The second problem is that with low thrust you cannot use the most efficient orbit change manoeuvres, as these require the change in velocity to be applied quickly. The closer to instantaneously the better. In practice, this means once the acceleration is below a 10th Earth gravity, then you need significant extra velocity to perform the manoeuvre, and in the case of very low thrust systems, the velocity required to change orbits can double. Now, the extra engine performance compensates for this extra velocity, and there is still normally a net gain, but also there is still a downside, which is the increased time it takes to do the manoeuvre. Journeys that would take hours or a couple of days now take months. Now, while this is acceptable with robotic spacecraft, after all we don't pay robots by the hour, it's clearly not acceptable when carrying people. So I'm going to rule out low thrust systems for human spaceflight because of these long transfer times, which leaves us with chemical and nuclear as the two options left. And if we use chemical systems, it means staging or refueling stops, which Elon Musk has selected for the underlying architecture of his Starship. So what does it have to do? The steps to get to places like geostationary orbit or the moon are typically a little over 4 kilometers a second. So any transport system will have to be able to do at least that before refueling. Here are some simple rocket equation sums for a vehicle to reach 4.2 kilometers a second using 3 different propulsion technologies. Methane oxygen is the fuel of the SpaceX Starship, and to make that speed requires 68% of the start mass to be propellant. Now, if the numbers in Wikipedia are to be believed, it can actually have a maximum propellant load of something like 85%. You can see from the rather simplified moon mission I used here to do the comparison that such an infrastructure requires something like 20 tons of propellant in low Earth orbit to get a ton of payload onto the moon's surface. There is a tanker version of the Starship, and for lunar operations, expect 95% of the Starship flights to be tanker flights. And as for getting a Starship to Mars, that takes more steps, so even more tanker flights. Hydrogen oxygen is what has always been assumed in the past for this sort of activity, and that needs 60% of the start mass to be propellant. At first sight, that may not seem to be much of an advantage over methane oxygen, but when accounting for the fact that propellant has to be carried to the refueling points itself in order to do the refueling, then you will see that the LEO propellant requirement is almost halved. But neither system can get anywhere near the potential of the Serpent engine, where, assuming no refueling stops, and accounting for real-life factors like the need to actually land using chemical rockets, the Scorpion needs 6.4 tons of propellant for each ton on the surface. And if one refueling stop is added on the return journey, this almost halves to 3.5 tons. And to take it further, at the Reinventing Space conference last November, I showed that it is possible to create a mixed infrastructure using specialist chemical landers which employ oxygen generated on the moon. This infrastructure could get the LEO propellant delivery to around 1 ton of propellant for each ton of payload on the moon's surface. And that is the first of the key arguments for the use of nuclear propulsion. The reduction in propellant delivery is not only a massive cost saving, but it also reduces the strain on the launch system. I know I argued earlier that we should be willing to accept much higher launch rates with reusable systems, but there are limits. With 50 support flights, Skylon can prepare a Scorpion in a couple of months for a mission. If this was raised to 200 flights, then we are getting close to a year, exceeding the mission duration in every case except interplanetary targets. It would turn the Scorpion into the space equivalent of a hangar queen, always being serviced and rarely flown. The next key advantage is that using nuclear propulsion extends the range of the infrastructure without the need for supporting refueling points or staging. This is a considerable help when using the vehicle as the vanguard to expand the boundaries of the infrastructure. The Moon is a good example here. The Scorpion can reach the Moon's surface and return without any supporting infrastructure, which is fine for a start. But if you add a refueling spaceport, then the payload to the lunar surface can triple, allowing much more serious exploitation of the Moon. And then further infrastructure can be added to make further improvements. The point here is that you need a start-up transport infrastructure before all the spaceports and the like can be established. And the final point is the performance margin nuclear gives means the essential features for long-duration flights, like proper radiation shielding, artificial gravity, escape systems, can all be incorporated. Whereas with chemical systems, the mass impact means they cannot. Given everyone's first concern when nuclear is mentioned is the potential danger, it is perhaps a little ironic that I am saying, as one of my key arguments, that it allows for safer transportation systems that do less damage to the crew and passengers. I've become more and more convinced as I have progressed this work that the very heavy investment, and that means something like $20 billion, that would be required to develop an engine like the Serpent would repay itself many times over. Any chemical-based infrastructure, however advanced, becomes swamped with the propellant requirements to support it. Now, with a nuclear-based infrastructure, the propellant requirements still dominate, but at least it would appear to be manageable. Returning to those long-term scenarios with hundreds of millions of people living in Earth orbit, these would need a transport fleet of around 10,000 vehicles, which is comparable to the current terrestrial civil airliner fleet. Serpent-powered vehicles can do this, although I suspect specialist passenger, cargo and tanker versions would make more sense than the general-purpose jack-of-all-trades Scorpion. And I would expect a significant number of electric propulsion systems for the cargo that can accept the longer travel times. The point here is that with nuclear propulsion we can see a route to expand human activity in space in a way that will never be possible if we confine our space transport infrastructure to chemical propulsion. Now we come to the last subject I would like to consider this evening, which is the standardization of the physical interfaces in the infrastructure, a subject where I despair of our industry. Okay, I have to own up and admit that no one has actually commented on this issue, but they should have done. The interfaces between transport systems, stations, support platforms, servicing facilities and payloads is the most important feature of an infrastructure, and the most important one to get right. Indeed, standardized interfaces are essential as they both create and define markets. A space infrastructure is a service market for applications customers, but that market only consists of customers and infrastructure that share interfaces. In the space field, we can see an excellent example of a standard creating and defining a market with CubeSats. There is no special technology that makes CubeSats possible. It is the existence of a physical standard, which means satellites can be made with the confidence that they can be launched. Elon Musk, Jeff Bezos and the space agencies can all completely mess up the space infrastructures that they are creating, and, as you have probably gathered, in my cynical, opinionated and purist view, they all are. But in the long term, it does not matter. Someone will get it right eventually, and the only long-term impact is a considerable waste of time and money. But the physical interface standards that come out of this cesspool of idiocy are things that we inflict upon humanity forever. And the key standards in this regard are the standards that structurally connect two systems together: the launch system interface, the docking system, and the berthing system. These could be separate standards, although I would argue that they could and should be just one standard. But it is the docking standard in particular that, once it is set, is for all practical purposes impossible to change. I don't know if we will ever have a Starship Enterprise or its like centuries from now. But I know if one does ever exist, the one thing it will have is the docking standard we select now. Unless, of course, we establish a standard that prevents the Starship Enterprise from happening in the first place, and guess what? That is precisely what we have done. And here it is, the International Docking System Standard, and that has been defined over the last decade. We use international in the American sense of the word. That is, America decides what it will be, ignoring its partners' inputs in the process, and then expects everybody to follow what it has dictated. The first point to make is this new standard provides no advantage in cost, function, or performance over the existing docking ports that have been used until recently on the space station. The new International Docking System Standard even works in the same way, so you have to be a real expert nerd to spot the difference. But they are different enough to be incompatible, so in July 2016, the SpaceX Dragon supply capsule delivered an adapter to turn the androgynous peripheral attach system into the International Docking System Standard to do exactly the same job. So what's wrong with it? I'm only going to highlight one of its many flaws this evening, and that is the hatch, which is only 80 centimeters in diameter. This is a legacy from hatches on the Soyuz spacecraft, and is thus a hatch size designed for early experimental test vehicles and not for a permanent working infrastructure supporting activities like large experimental facilities such as the International Space Station. The problem with a small hatch is the many things that you cannot get through it, starting with a NASA spacesuit, and the Russian spacesuit can only get through it with great difficulty. It means a spacesuited astronaut cannot get in and out of a habitation area, and that severely constrains the ability to deal with depressurization emergencies. I confidently predict that if we stay with the 80 centimeter hatch, someone in the future will die as a consequence. The second thing wrong with the hatch size is that you cannot get a standard equipment rack through it. The whole internal architecture of the American, European and Japanese elements of the space station are based on these racks, and it is an essential part of the concept that they can be removed and installed in orbit, which means being able to get them through the cargo supply system hatch. So of course, if you were to be investing €2.5 billion into creating the biggest international supply vehicle, and using a module structure that is based on the standard equipment racks, you would not be so stupid as to put an 80 centimeter hatch on the front, would you? And even if you had been that stupid, you would not repeat the mistake on the next generation space station, would you? I saw this proposal for the next space station from a German-US team at the Bremen International Astronautical Congress in 2018. And I asked the nice man who was on the team how they were going to get the experimental racks into the free flyer bit or into the large Bigelow module if they were only using the International Docking System Standard for all the module-to-module connections. He admitted this was proving a bit of a problem and they were looking at solutions. Well, for myself, I can't see the issue here. There is only one solution, and that is don't use the International Docking System Standard. And in case you're wondering how the International Space Station overall has managed with 80 centimeter hatches, the simple answer is it hasn't. There are several berthing ports which have 1.3 metre square hatches, which standard racks and much else besides can easily get through. Another thing you can't get through the hatch is somebody in a wheelchair. Now, this may sound silly. Well, firstly, it isn't silly if you're in a wheelchair, and secondly, it shows into sharp relief that we should be considering a standard for a space infrastructure that is intended for use by all humanity, not just selected professional astronauts. So how did the Scorpion get round the problem? Well, I took my own advice to the DLR engineer and just did not use the International Docking System Standard. Rather, I used something called the Universal Space Interface Standard, or USIS, which came out of the Skylon requirement validation studies, and I have been trying to plug this idea ever since. It is not yet a fixed design, and here are 3 concepts from 3 different design teams trying to embrace the USIS vision. And following good system engineering practice, that vision is laid out in a purpose statement with accompanying objectives. Good practice that it would seem the team developing the International Docking System Standard failed to follow. Indeed, one has to wonder if they did any requirements generation work at all to establish what the requirements for a future docking and berthing system should be. When I asked a senior member of ESA, who was supposed to be partners in the development of the International Docking System Standard, whether it would be possible to have a look at the requirement specification to see if I could get my head around what seemed from the outside to be bizarre decisions, his reply was, "Yeah, we'd like to see that as well." The key feature of the USIS is that it is based on a standard connection ring, which is probably close to 1.6 meters in diameter, which in its simplest form can be a launch system interface ring, so as a consequence, anything being launched into space has the interface standard connection without it having to be specially built in. And in its most complex form, the USIS is a full docking system with a pressurized hatch. The Scorpion has a total of 12 USIS connections for the system of various sorts. It uses it for the docking, for the payload connection, the capsule connection, and the connection point for the Serpent engine's reactor servicing system. The USIS is a critical element in what makes the Scorpion work. If I'd used the American alternative, I could not get the equipment inside during construction, I would have to use something different to connect the payloads, and so on. In short, it would have been a complete mess. To sum up, I had many objectives with the Scorpion study, but at its heart it is an exploration of the space infrastructure and what it could be, a subject that has always been my passion and at the heart of my career in astronautics. Although the Scorpion is unashamedly a piece of Buck Rogers, I hope that I have convinced you that that is no bad thing. It explores questions like what is the best launch infrastructure architecture? What technologies are needed to create a space infrastructure that does not constrain what we can do in space? How do we future-proof future standards that we are now setting? But above all, I hope it is an inspiration, showing what space infrastructure it is possible to achieve, not through any technology breakthroughs, but simply a more intelligent use of the technologies that we already have.